Welcome! In this video, we will use the variational principle to study the hydrogen molecule ion, and we will determine whether this molecule ion can exist at all, and if it is, what is its energy, right? And in the process, we will also solve problem 7.8 as it appears in the third edition of Griffiths' Introduction to Quantum Mechanics. So let's dive straight in. Now, the hydrogen molecule is H2. Right? 2 protons, 2 electrons. But we are interested in the ion, which will be a simpler case. It only has 1 electron. Now, this is basically one proton, and 1 electron that is bound to the system. And that's exactly what we want to figure out. Is it possible to have this configuration? If we bring in a proton, does it actually bind? Will there exist a bound state? That's what we want to determine. So to do that, we'll have to find the energy and then compare it to the energy of just an electron and just a proton to see if this is viable. Okay, so how do we do this? Well, this is the variational principle that we will use because, of course, solving the exact Schrödinger equation will be a nightmare. So let's build a Hamiltonian. Now, the Hamiltonian for this would be, of course, a kinetic part for the electron. And then we will have 2 Coulomb interactions, right? One with each one of these. So we will get minus, they're negative, minus e squared 4 pi epsilon 0. And we will call the distances R1 and R2. Of course, it doesn't matter which is which, but those will be the names that we will use for our coordinates. So R1 plus 1 over R2. Okay, and finally, there will be an interaction between our protons. So they will be some distance r away, and we will want to figure out what this distance is, right? We want to know if they can bind, and if they do, how far away will these protons be? So we can use that to write the Coulomb term for the protons, which will be 1 over big R. That will be fixed. We don't know what the value of R will be. We may have to play around with it, but once we have determined it, it should be a fixed value. Okay, and now we need to figure out a wave function. What will be our trial wave function? Well, we could work with the wave function from the hydrogen atom because this is basically 2 hydrogen atoms combined. Right, so this is 1 over pi a cubed square root. This is the ground state wave function for the hydrogen atom. And we can take basically 2 of these because we have now 2 hydrogen atoms, kind of. And we could use a technique that is called LCAO, the linear combination of atomic orbitals. And we will use that, so this we'll call just psi, the ground state for one of them. So our wave function will be a linear combination of the hydrogen atom number 1 and the hydrogen atom number 2. So basically, psi g of R1 plus psi g of R2. This is basically, we have 2 hydrogen atoms at the same time. That's basically what we are saying here. Okay. So now, of course, we need to determine the normalization constant. Okay, what is A? So that will be done as usual. It will be a long process, I warn you. So 1 is equal to the integral of this thing conjugate, right? So psi g R1 plus psi g R2 conjugate. And now the exact same thing, but normal. So psi g R1 plus psi g R2. The R3, of course. Okay. Now we multiply through. And by the way, of course, don't forget the a square. Now we multiply through and we get, first of all, psi g conjugate of R1 and psi g of R1. But what is this? This is going to be 1 because we are dealing with the hydrogen atom and the wave function is already normalized, right? For each individual hydrogen atom, not the, sorry, dropped my pen, not the total one. So this right here will simply be 1 in a moment, once we take the integral. So maybe let's do it like this, and dr3. Then we have another integral from the cross terms, right? We will get psi g r1 conjugate times psi g of r2, and also we will get a term that is psi g conjugate of r2 times psi g of r1. And finally, we will get an integral that is only with the psi g of r2. So psi g conjugate of r2 times psi g of r2. So this integral will also be 1, right? It's normalized. This integral will be 1, as I mentioned. And these two terms are going to be equal, actually, because our wave function for the hydrogen atom is real. So that means that psi g conjugate is simply psi g. Whoops, went a bit too far there. And psi g r2 conjugate is also psi g r2. So that means that this thing here is simply 2 times one of them. So there we go. So that means that 1 is equal to a squared times 1 plus 1, so we get 2, plus 2 times this integral right here. So integral of psi g of r1, psi g of r2, dr3. So that is now the integral that we need to solve. Let's call it I. Very creative. Okay. So let's write what the psi of g is. So this would be integral of 1 over square root of pi a cubed times e to the minus r1 over a, and the exact same thing for the other. So square root of pi a cubed times e to the minus r2 over a. And now dr3, we are in spherical coordinates. So let's write it r squared. The question is r1 or r2? The answer is it doesn't really matter. But let's take a moment to see which coordinates we want to use. Maybe let's change colors, green or something. So let's go here to the side. So our system is as follows. We can align one of our protons here in the origin and one proton in our y-axis and distance big R away, right? We said that the distance here will be big R. And our electron is going to be here floating around somewhere. And we also mentioned that these distances will be R2 and R1. Again, it doesn't matter which is which. And if we are in spherical coordinates, then this angle right here is going to be theta. We can align it for it to be theta. So under this configuration, we can then just use the law of cosine to write R2 as the square root of R1 squared plus big R squared minus 2R1 R cosine theta. So by doing this, we are only left with the coordinates of system number 1. So let's now replace this into our integral, and we can now just stick to our notation of R1. So R1 squared sine of theta, right? All of this coming from the fact that we are integrating in spherical coordinates, dr1, d theta, d phi, and R2 will be R1 squared plus big R squared minus 2 times R1 R cosine theta. Okay, amazing. Wait, I just noticed that I put this random e in the middle. I don't know what that was all about. Okay, so this is what we now have to integrate. So the question is, well, how do we do it? Well, the phi integral is trivial. There's not really much to say there. The theta integral is doable, but not particularly fun. But the r integral is at this moment basically impossible to do. And by the way, it might be easier to, since there's only r1 now, it isn't really necessary for us to make a difference between r1 and anything else. So let's just call it r. That way we don't have to write the subscript anymore. So the easiest integrals to do here are, of course, the phi integral and the theta. So the phi we can do right away. There's no phi dependence, so we get 2 pi. Remembering that the limit goes from 0 to 2 pi, of course. Then we can pull the constants outside. And then we get integral from 0 to infinity, integral from 0 to pi of e to the minus r over a, e to the minus r squared plus big R squared minus 2r big R cosine theta. Okay, over a. And then we get r squared sine theta dr, actually the other way around, the theta dr, because of the order I wrote this in, but it doesn't really matter in the end. Okay, so how do we integrate this? Well, notice that in the exponent, we have a function of theta that is inside a square root, and outside, right here, just floating around, we have a sine, which is the derivative of cosine. So for that reason, it might be useful to use a substitution in the exponent to get rid of that annoying square root. And when we have to take the differential, it's going to include a sine of theta that is already here. So let me show you. Let's call u square root of r squared plus big R squared minus 2rr cosine theta. Calling u just the inside wouldn't be a good idea, because then you would be left with u to the square root of u, which would be super annoying. Now we can write this as u squared is this thing without the square root. And now we can easily take the differential. 2u du is, well, big R and small r, they are constants from the point of view of the angle. So they will be 0. And then we get the derivative of cosine, which is minus sine. So we get 2 small r, big R, sine of theta d theta. So in the integral, we already have r sine theta d theta. So from here, we can see that u du divided by big R is r sine theta d theta. Okay, and how do the limits change? Well, theta used to go from 0 to infinity. So if theta is 0, let's now plug it in here. Well, you have to consider with a square root, right? So u is the square root of this thing, right? So if theta is 0, then u is going to be square root of r squared plus big R squared minus 2rr, because the cosine of 0 is 1. But you can rewrite that as the square root of r minus r squared, which is the absolute value of r minus r. And now, don't forget about that absolute value, because the value of small r goes from 0, which is smaller than r, to infinity, which can be greater than r. So you can't just forget about it, okay? It's very important that you don't make that mistake. Then, for the upper limit, theta goes to pi. And in that case, u will be square root of r squared plus big R squared plus 2rr, which is the square root of r plus r squared, which is simply r plus r. Now, in this case, there is no need for an absolute value, because this quantity is always positive. There's no room for this to be negative, right? In that case, it can indeed be negative. if small r is smaller than big R. Okay, so now let's plug all of that into our integral I. So this will be 2, the pi's cancel out, divided by a cubed, integral from 0 to infinity, and then integral from absolute value of r minus r to r plus r. And then, well, the exponential stays the same. One of these r's survives, the other one doesn't. I mean, the other one is already inside of our change of variables. And then we get e to the minus u over a, and then u du dr, right? That thing is u over a, 1r. Oh, and don't forget about this divided by r. So there's still 1 divided by r here. Okay, did we forget anything else? U du over r is r sine theta d theta. No, I think we're fine. Okay, so now we need to figure out what the u integral is. So let me just go here off to the side and call it IU maybe. So IU, this is the integral from r minus r to r plus r. So r plus r of e to the minus u over a u du. Okay, so what is that integral? Well, we can solve this by using integration by parts. So we can say, I don't know, u prime, this is going to be u, and du prime is thus du. dv, we can choose it to be e to the minus u over a du. So then if we take the integral of that, we get minus a e to the minus u over a. So now let's plug it in. So we get minus au e to the minus u over a evaluated between absolute value of r minus r, I forgot that line, and r plus r. Then we get minus the integral, so we already did that, the integral of this product. So we get minus minus, so plus, and a goes outside, and we get integral r minus r, r plus r, e to the minus u over a du. Okay, so now let's continue this down here. So let's plug in the respective values. Minus a, the upper echelon here, will be r plus big R, e to the minus r plus r over a, and then minus the other one. So we get minus minus, so we get a positive. That would be a times the absolute value of r minus r, e to the minus absolute value of r minus r over a. And then this integral right here. Do I still have room to my right? Not too much. So let me continue down here. So this integral will be plus a times. Now the integral of e to the minus u over a is minus a times e to the minus u over a, evaluated at the endpoints. So let me now just plug that in. So plus a times, the first one will be minus a times e to the minus r plus r over a, and then we get minus minus a e to the minus absolute value of r minus r. All right. Now let me get rid of this one. It was just an intermediate step. And we can factor this out. So I will write it here now. So we can factor it out as minus a squared e to the minus r plus r over a plus a squared e to the minus, oh, there's an divided by a missing, minus r over a. Make sure to be very clear whenever you are writing your absolute values, so you don't confuse them with normal parentheses. Okay, now let's factor this out. So first of all, notice that we can factor out an a from all of this. So a times everything else. Then we have two different exponents, right? We have e to the minus r plus r over a. And if we factor that out, we get this thing right here. So minus r plus r. And so that's this part. And then we have this. So we get minus a. And then we can factor out all the other ones. So e to the minus absolute value of r minus r over a. And if we do that, we get r minus r here. So absolute value of r minus r plus a. Okay, and there's minor adjustments we can make here. So we can factor out a minus sign here, for example. It isn't a huge deal, but it's gonna make it a little bit prettier. So okay, and this is the result. So this is what we now will plug into what we had before. So instead of having this thing, now this r e to the minus ra, they still remain. So I will rewrite them here. So r e to the minus r over a. So that still remains. And now I just plug in all of this. But notice that this a here, well, that will cancel out with the a's that are in front. So instead of having a cubed, oh, I'll just rewrite it. We will now have a squared r. Okay, so now let me copy this. So we get minus e to the minus r plus r over a, factor of r plus a, plus e to the minus, oh, there's a parenthesis missing, r minus r over a, r minus r plus a. The r, of course. Okay, now with this, we can begin solving the r integral. Let me get rid of some of these parts that are protruding. We don't really need it anymore anyways. Okay, so the r integral, notice that we have this absolute value in here. And that is very, very important to note because we are integrating from 0 to infinity, and the absolute value, its value depends on the value of r, okay? So if r is smaller than r, and big R, then, actually maybe do it like this, then the absolute value will be minus this, because if this smaller r is smaller than the big one, then we will have a negative number, and we're not supposed to get a negative number out of an absolute value, so we have to put a negative sign in front. So that means that we get minus r plus big R. And in the other scenario where r is greater than big R, then there is no problem, it will always be positive. So in that case, we simply take the absolute value out and we get r minus r. So there are two scenarios. When r is between 0 and big R, which is case number 1, right, that one. And we also have the case where r is between big R and infinity. So we have to split up our integral. Only when there's the absolute value, of course. When there is no absolute value, there's no need to split it up. Okay, so I hope that this logic was clear. Now let's do it. So let's split up the integral. So first of all, we have our constants, blah, blah, blah. Okay, now integral number 1, this one goes from 0 to infinity. This is where there is no absolute value. There's a negative sign here, don't forget about it. So minus, and then we get r e to the minus r over a, e to the minus r over a, e to the minus big R over a. So notice we have this right here, which is a constant. We can pull it out of the integral. So I'm gonna use the space better here. So minus e to the minus big R over a. And these two we can just add up. So we get minus 2r over a. Okay, so doesn't really look too pretty. I'm gonna rewrite it. So minus 2r over a. And then of course times these constants, r plus big R plus a dr. Okay. Alrighty, next we have, this is the more problematic part, right? We need to split up the integral. This time we go, let's start from 0 until r. In that regime, small r is smaller, so we have to add the minus sign in front. So that means we get e to the minus this thing. So that minus sign goes away, so we are left with r over a basically, times e to the minus r over a. But we still have to consider, oh, by the way, plus, there is this r times e multiplying. So we will have an r and e to the minus r over a. So basically, these exponentials will cancel each other out, and we have this constant in front. So again, I'm going to rewrite this. E to the minus, or is the positive here? Sorry. We are in this case. No, it's minus. It's okay. Okay. Good. And now everything else. So we get, now here, of course, minus in front. So we get positive big R, negative small r. And of course, as r is smaller, if r is smaller, then this is positive and all is good. dr. And now comes the last interval between 0 and infinity. Now in this case, what do we have? Now, this same thing, but, well, first of all, let's include the r and e to the minus r over a that are in front, right? Again, these ones. Don't forget about that. And now, let's consider everything else. So we will get e to the minus r over a, e to the plus r over a, and then in parentheses, r minus r plus, oh, by the way, sorry, this is from r, my bad, sorry. So this is from r to infinity, that's my bad. So r minus r plus a, dr. Okay, so the constant can go out here, e to the r over a, and just as before, this will simply be e to the minus 2r over a, and just rewrite everything here. So r minus big R plus a dr. So this is these are the integrals that we have to solve. There are 3 integrals. So let's label them accordingly: I1, I2, and I3. All right. So, let's solve I1 first. I1 is this interval right here. So 0 to infinity. Well, I'm not going to rewrite it. We can see it right there. So how do we solve it? Well, using integration by parts. So let's call u is going to be everything that is not the exponential, right? So r times r plus a, and thus du will be, well, we integrate this, so we derive that, so we get r plus a, and then plus r times the derivative of that, which will be simply 1, so plus r. And of course dr, so we end up getting 2r plus r plus a, and all of this dr. Okay, and the v, this will be the exponential, so minus 2r over a dr, and v will be minus a over 2 e to the minus 2r over a, and that's it. So now let's write down I1. So I1, this will be now this product, so we get minus a over 2 times r plus big R plus a, and then the exponent, so e to the minus 2r over a, between 0 and infinity. But in both of these limits, this will be 0, because at infinity, the exponential goes to 0 faster than the polynomial, and at 0, the exponential is 1, but you have 0 here, so everything is 0 anyways. So the first term is simply 0. Now the second term comes from this product, and it is minus in front, right? So we get minus minus, a positive, and the integral from 0 to infinity of, now we get a over 2 in front, and then we have 2r plus big R plus a, e to the minus 2r over a dr. Okay, and here we have to use this technique, right? Integration by parts again. So let's say, once again, u will be 2r plus r plus a, du will be 2 dr, and on the other side, we have the v, which will be e to the minus 2r a dr, and v will be minus a over 2 e to the minus 2r over a. So I1 will be a over 2, the one that was lingering from before, times, and then what we have, then we got u times v, these two, the product of these two evaluated at the endpoints. So we get minus a over 2 times 2r plus big R plus a times the exponential evaluated between 0 and infinity. Now at infinity, this thing will go to 0 because of the exponential. Well, actually, I'm gonna do it step by step. Let's finish this and then we will find out the value. And then we have minus this product. So minus minus gives us a plus. And then we have the integral of the product of these things. Now 2 cancels out with 1/2. So we are left with an a, integral from 0 to infinity of e to the minus 2r over a dr. Okay, so now let's calculate this. So we have a over 2 minus a over 2. Well, as I mentioned, at infinity, this is 0. So we only have the second term. So we get minus in front, which will cancel this minus. And then we have 0, so this part is 0, times r plus a. And then we have this integral, which will be minus a, minus because of this integral, we get a over 2 minus a over 2 when we integrate e to the minus 2r over a between 0 and infinity. And in this case, at infinity, once again, it goes to 0, but at 0, this thing is 1. So for that reason, the exponent goes away and this minus turns into a plus, right? Because it's minus the evaluated at 0. So now we can simply find out the value. Let's see, just multiply everything through. We can actually factor out a over 2 to make it simpler. So we get a squared over 4 factor of r plus 2a, right? Yeah, 1a here, 1a here. So this would be r a squared over 4 plus a cubed over 2. Correct? I think so. Okay, so that is I1. So we will later plug it in here, and don't forget about that minus sign in front. Now let's go for integral number 2. So integral number 2 will be quite a bit simpler. I will actually write it down here because it will be quite fast. So integral 2 is integral from 0 to big R of r minus r plus a dr. So this one, as you can see, is simply a polynomial. So easiest way for me is to just write it out. So we get minus r squared plus r plus a, right? This is everything that only has one r, and all of this dr. So simply, the first part gives us minus r cubed over 3, and then we get plus r plus a over 2 times r squared. So let's multiply through, and we get minus r cubed over 3 plus r cubed over 2 plus a r squared over 2. So basically, we can add these two together, minimum common denominator. So we get minus 2r cubed plus 3r cubed over 6 plus a r squared over 2. So here we get r cubed over 6 plus a r squared over 2. That is the result of the second integral. Okay, so now we go back here. We have already solved this thing. Now, just a quick reminder, what are we doing? We are still trying to find the normalization constant of our wave function, by the way. That's all we are doing. We haven't even started with the problem, just putting it out there. We are still finding the normalization constant. So finally, we need to integrate I3. So I3, let's use green. Actually, I'm going to do it down here. So I3, this is the integral r to infinity of r e to the minus 2r over a, r minus big R plus a dr. I will use the exact same technique that we used in the first integral. So I will use substitution. I will say u is r times r minus r plus a. You can't see this. Wait a minute. There we go. And du will be, again, so derivative of the first part plus the rest. So, I mean, times the rest, plus the first part times the derivative of the rest. So this will leave us with 2r and all of this dr. And dv, as usual, is the exponential. So v is e to the minus 2 over a, times, of course, minus a over 2. So now let's continue. So we get this first product, which will be minus a over 2 times r minus r plus a times e to the minus 2 over r between big R and infinity. And then we get the second part of the integration by parts, which is minus this thing. And there's also minus here, so we get plus a over 2 integral of 2r minus big R plus a exponential dr. Okay, so now we need to integrate by parts again. So here we will use u is 2r minus r plus a, du is 2 dr, and dv will be the exact same thing. So e to the minus 2r over a dr, and thus v will be minus a over 2 e to the minus 2r over a. Okay, let's plug it in and let's solve this first part. So at infinity, this thing is 0 as before. So let's plug in at r. So we get minus, so plus a over 2 big R, and then r minus r, that cancels out. And then we have this a here, so we get a, and e to the minus 2 big R over a. Good, now the rest. Plus a over 2 and the thing that relates to the whole integration by parts. So there, let's see, we get this product, which will be minus a over 2 times 2r minus r plus a times the exponential evaluated between r and infinity minus another minus sign, so plus a over 2 times 2, so the 2's cancel out, the integral of e to the minus 2r over a dr between r and infinity. Okay, so now let's simplify this first part. We get a squared r over 2 e to the minus 2r over a. And then we have, oh, I missed the parentheses. We have a over 2 times. And now we have this thing evaluated at infinity, which is 0 again. So we are only left with the r part. This minus turns into a plus, and we get a over 2. And 2 big R minus big R is 1 big R. So r plus a, e minus 2r over a. And then this integral will give us minus a over 2 when we integrate the exponential. So we get minus a over 2 times the existing a, so we get squared, times e to the minus 2r over a between r and infinity. Whew, okay. Now, notice that every single part, actually, I'm not going to go there. I don't want to, not yet. I'm not going to skip any steps. So e to the minus 2r over a plus, now let's, I'm not going to multiply through just yet. So here we will multiply through. So we get a r over 2 plus a squared over 2. And then we have, both of these are multiplied by this exponential. So e to the minus 2r over a. And then we have this thing. So at infinity, this is 0. So we're only left with the second part. It becomes positive again. So a squared over 2 e to the minus 2 big R over a. So now I can indeed say it. Notice that we have e to the minus 2r over a everywhere. So let's factor it out. So e to the minus 2r over a, factor of a squared over r over 2. And now let's multiply through this a over 2. So we have here a squared r over 4. Then in the next one, we have a cubed over 4. And finally, we have plus a cubed over 4 as well. Correct? I think so. Okay, yeah, I think it is correct. So finally, we can simplify this a little bit. So we get e to the minus 2r over a. And then we can add these two together. So this is 2 over 4. So we get 3a squared r over 4 plus 2 times a cubed over 4, which is a cubed over 2. Okay. So this is I3. So now we calculated all three of them. We have I1 right here, I2 right here, and I3 right here. So let's plug all of that into our original equation, which is right here. So let's see. What is R1? R1, our result was, here it is, ra squared over 4. I'm going to zoom in just a little bit more. So ra squared over 4 plus a cubed over 2. Now let's plug in I2, which was, there it is, r cubed over 6. So r cubed over 6 plus a r squared over 2. And finally, let's plug in I3. So I3 is this thing right there. So that is times e to the minus 2r over a times 3a squared r over 4 plus a cubed over 2. Okay, and all of this, of course, is inside the integral. I mean, the original parentheses. So I'm gonna make some room Can I make this bigger somehow? No? Any second. There we go. So let's multiply through. Notice that here, for example, the exponents cancel out a little bit. And everywhere we have this e to the minus r over a. So let's factor it out. So we get 2 e to the minus r over a divided by a squared r. And then we are left with r. I'm going to go step by step because I don't want to make a dumb algebraic mistake after having done so much work. By the way, I already almost made one. There's a minus sign in here. Almost forgot about it. Minus here and minus here. R cubed over 6 plus a r squared over 2, and then plus 3 a squared r over 4 plus a cubed over 2. So here the a cubed over 2 cancel out, and these two add up, right? So we'll get 2a squared over 3 instead of 3. 2a squared r over 4, sorry. Okay. Now, let's simplify everything, or let's write it out explicitly. So we are left, we are left with r cubed over 6 plus a r squared over 2 plus a squared r over 2. All right. So now let's multiply through, right, by everything except for the exponential, e to the minus r over a, factor of, and first we have this r cubed, which now will be r squared. It is divided by a squared, and it is still divided by 3. Then we have the r squared goes to r. We are dividing by a, and the 1/2 cancels out. And finally, we have 1. And there we go. This is the integral that goes, this is the value of the integral that goes into the normalization constant. Now, where was it? Up there. This is where it went. Right? This is where it went. So let me just rewrite it quickly. So our result here is that 1 is equal to a squared 2 plus 2i. Now let's solve for a. So a squared is 1 over 2 plus 2i. And I is, as we just saw, e to the minus big R over a, factor of, I think it was 1 plus r over a plus r over a squared times 1/3. So this is the big result. Okay, so that is the part due to normalization. We normalized our wave function. Congratulations, it only took us 50 minutes. Okay, so now I'm gonna make some room. Okay, so now that we found the normalization constant, we can actually begin solving the problem. So let's go ahead. Now, this Hamiltonian right here is the one that we now need to find the expectation value of. Okay, so now this Hamiltonian, we need to sandwich between our wave functions to actually find the energy that we're looking for. So we want to construct this. Now, because our wave function is quite big, the Hamiltonian is quite big, I don't want to have to write down the entire thing at once. So I will begin, so step number 1, I will simply find h acting on the ket of our wave function. And then I will put the bra in there as well and finish it off, right? So h acting on our system, that will be h times a, so maybe I'll write it like this, h acting on psi, This is h times a, and then we have psi g r1 plus psi g r2, which will be simply a times h acting on psi g of r1 plus h acting on psi g of r2. But now take a look at what this whole thing is. Okay, let's put the value of h in here. Let's write it everything here. So h ket will be the constant a times, now we have minus h bar squared over 2m del squared, and then we get minus e squared 4 pi epsilon 0 times 1 over r1. Well, of course, there's also the 1 over r2 part. And psi g r1. And now the exact same thing. So minus h bar squared, 2m lambda squared, minus e squared, 4 pi epsilon 0, 1 over r1 plus 1 over r2. And we still have to include this part. So we get plus e squared over 4 pi epsilon 0 r factor of psi g r1 plus psi g r2. Okay, now notice what we have here. So I'm gonna use the first one as example, and the second one we will do the exact same thing. So we have minus, by the way, there we go. There we go, psi g of r2, sorry. So minus h bar squared over 2m del squared minus e squared 4 pi epsilon 0 1 over r1 acting on psi g of r1. What is this? What is this? This is the Hamiltonian of the hydrogen atom acting on the wave function of the hydrogen atom. This is h acting on psi 1, which we know is E1 acting on psi 1. So we can replace all of this by E1 psi 1, which is a huge relief. However, we haven't dealt with everything. We still have this minus e squared 4 pi epsilon 0 r2. Actually, I'll write it separately. So 1 over r2 times psi g of r1. So we still haven't dealt with this. Okay. Now, the exact same thing applies for the second one. So this will also be plus E1 of psi 2. Actually, instead of psi 2 and psi 1, I'm going to stick to the notation psi g of r1 and psi g of r2. Okay. But here there will also be this extra term, which will be minus e squared 4 pi epsilon 0 1 over r1 this time, because that is the one that isn't included in the Hamiltonian for r2. And of course, the extra term here that hasn't really done much. Plus e squared 4 pi epsilon 0 r psi g r1 plus psi g r2. Okay, well, and there's another parenthesis at the end. Okay. So we are making some progress. Now, before we continue, there is something we can do to make this look better. So we know that the sum of psi g r1 and psi g r2, that is simply psi, right? That's literally what we defined psi to be, somewhere over here, right? We said psi is a times this. Well, we actually said it's a also. So maybe let's write it as psi over a. So, and it will cancel out with the a that is out here, but I just don't have to write it out the entire time. And similarly, we have E1 times psi g R1 plus psi g R2. So we can factor it out as well and write it like this: psi and divided by a. So that just makes notation a little bit cleaner. So this is h times psi. So now let's add the bra. So now let's add bra psi. So when we do that, we will get a squared in front. And then we have, well, psi times all of this. Actually, let me not write it out explicitly just yet. So I'm actually going to leave it like this. And then we have psi times this. So E1 over a psi minus, then we have minus e squared. This is a constant. I can take it out. And then we get psi 1 over R2 psi g of R2. So I'm going to leave it like this. And then we have this part. So minus e squared 4 pi epsilon 0 psi. Actually, let's do it correctly. Psi. I have been a little bit sloppy with the notation so far. Psi g of R2. And finally, we get plus e squared over a 4 pi epsilon 0 r times psi. And here there we go. So this is also psi, which of course is simply going to be 1, right? So we don't really need to write it out. Okay, it is normalized by definition. All right, so now let's start multiplying through by a. So we get E1 here. Then we get minus e squared 4 pi epsilon 0 times a. And now what we will do is we will replace psi by what it is, right? A times psi g of R1 plus psi g of R2. So we will get a squared, and then we get psi g of R1 plus psi g of R2. All of this sandwiching 1 over R2 and psi g of R2. And the exact same thing here. So minus e squared over 4 pi epsilon 0 times a squared. And then we get bra of psi g of R1 plus psi g of R2. And then we have close parentheses 1 over R1 psi g of R. This time it's, oh, sorry, last time it was R1, not R2. That was my bad writing, yes. Sorry. R2. Okay. And there's no parentheses anymore. Okay. So there's still a few things we can do. So we can start by factoring out all of these constants. So minus e squared, let's write the a out in front. I like it that way. And all of this will now be factoring. And now let's multiply through here. So we get bra of psi g of R1, 1 over R2, psi g of R1. And then we get the other one, which will be psi g of R2, 1 over R2, psi g of R1. And now the same with the other one. I'm going to write it down here because I don't have that much room. So plus, and now I multiply the right one. So I get psi g of R1, 1 over R1, psi g of R2. I forgot the parentheses there. And now the other one, so psi g of R2, 1 over R1, psi g of R2. Okay, phew. And now notice the following. We have two types of these inner products. One is psi g R1 with 1 over R2, and the other one is basically the same R's here with a different R here. And then we have different R here, different R here. But notice that the wave functions are the same. So basically, these two are exactly the same. They're going to give you exactly the same results. The protons are indistinguishable. You can simply make a change when you're doing the integral, for example. You can change the name R2 to R1, and you're going to get exactly the same. Okay, so basically, what we have is not 4 different integrals, but we have 2 different ones. Right? Because these two are the same and these two are the same. So we get 2 times psi g of R1 over R2. You can leave whatever name you want. It doesn't matter, as I mentioned. If you are unsure, you are welcome to solve them all, but you are going to be doing the work twice. I'm going to show you how to do it once. If you want to do it again, I mean, sure, but there's no need. Plus 2 times now the cross terms. So psi g of R2, 1 over R2, psi g of R1. And we can, of course, factor out these 2's and leave it there. Now this is what in Griffiths' book is called the d and the x integrals. So the direct integral is this one. I don't really know why it's called direct. If you know, you can leave it in the comment section. I honestly don't know. So this is that. And then there is the exchange integral, which is that one. And this is where we begin with Griffiths problem 7.8. Because now we want to figure out what each one of these integrals is. So strap on. Whew. Okay, so let's begin with integral d. So d is the integral of e to the minus r1 over a. Well, in case you just joined, I'm using that our trial wave function was the sum of these hydrogen wave functions, which are of the form e minus r1 over a divided by square root of pi a cubed. Just a quick reminder. So we are dividing by pi a cubed and the square root. And then we have 1 over r2, so times 1 over r2. And then we have the other one, so e to the minus r1 again, so r1 over a, and divided by square root of pi a cubed. All right. And of course, we are integrating in spherical coordinates. So we need to add this r2 or r1 squared sine of theta dr d theta d phi, just as we did before. But this time, we already have our 1 over r2. And remember, what we did last time was that we did the following. I'm going to show you in case you just joined. So we have two protons, one here, and we align our axis like this, so that proton number 1, this one, is at the origin, and our electron is somewhere over here. Totally not to scale, by the way. This distance is r, and this distance is r1, this distance is r2. So we can find one in term of the other. We can easily change labels, by the way, which is what we did before. There's no difference. So what is best for us? If you write as before, r2 is equal to r1 squared plus r squared minus 2r1 r cosine theta, right? If we choose that coordinate, then we will have an integral of 1 over this monstrosity. And I don't really feel like doing that. I'm going to be honest. I'm going to fight that. Oh, by the way, this is squared, by the way. I'm going to fight that to my last day. Okay, I'm not going to do that. So for that reason, I'm going to this time change the names. This time, R2 is this, R1 is this. As I mentioned before, it doesn't matter. So there we go. So we simply change the names. This will be then R1. Sorry, what's going on? R1 and R2. So that means that now we get rid of R1 and we are only left with R2. So we are going to be using the R2 coordinate this time, in contrast to what we did before. So this will be integral, all three, of course, 1 over pi a cubed in front, e to the minus 2 over a times the square root of r2 squared plus big R squared minus 2 small r big R cosine of theta. And then we have r2 squared divided by r2. So we are left with only r2. And sine of theta dr, dr2, of course, d theta d phi. The good thing is that, well, actually before that, let's agree there's only one r, so no need to use the subscript 2. Okay, so r2 is simply r now. Previously, I had forgotten to put a 2 there, by the way. It isn't a big deal. We simply changed the name now because it's easier to write it like this. And now let's use the same change of variables as before. So the easiest way to go about this is to solve, well, the phi integral first, of course, because that's simply 2 pi. But after that, let's say, well, let's go for theta first. And now let's call u the entirety of what is here. So again, square root of r squared plus big R squared minus 2r cosine theta. And so we square this. But, well, the square root was there, by the way. Now we square it, take the differential. The small and big R are constants when you look at them from the point of view of the angle. They don't change with the angle. So we are only left with this part. Derivative of cosine is minus sine, so the minus cancel out. We get 2 small r big R sine of theta d theta. So from here we can find that u du divided by big R is r sine theta d theta, which is precisely what we have here and here. So we can now put this back into this direct formula, the direct integral, sorry. 1 over, actually, we already solved the pi, so let's include 2 pi. So 2 pi over pi a cubed. Let me turn off the notifications. There we go. And then we have 1 over r coming from here. Integral from 0 to infinity. And what are the bounds of this new integral, by the way? It's going to be just as before. Theta used to go from 0 to pi. So when theta is 0, just as before, u will be absolute value of r minus r. And if theta is pi, then u will be r plus r, exactly the same as before. If you joined in because you only want to see this problem, the reason behind this is that if you plug this in, theta 0, you get r squared plus r squared minus 2rr, which is r minus r squared. It is inside the square root, right? Because you want u, not u squared. And then you get the absolute value. And that is so important. Don't forget about the absolute value, please, right? Because this can either be positive or negative. Small r varies. It can be smaller or it can be greater, okay? If you're still unsure, go back to the chapter of the change of variables, and I explained it in greater detail there. Okay, now this goes from r minus r to r plus r. And then we have e to the minus 2 over a u du dr. Okay, and this time, unlike before, we don't have the extra r lying around, right? Nor do we have the extra exponential. So let's solve this. I mean, we already solved this before, actually, but I erased it, so I guess we're gonna have to solve it again, but it's fine if you just joined in. I will show you how to do it. So let's call this IU. So IU. This, we will use integration by parts. So let's call u prime is u, du prime is du, dv is e to the minus 2 over a u du, and v is minus a, okay, that looks terrible, minus a over 2 e to the minus 2 over a. Okay, so now the integral itself will be the product of these two. So we get minus a over 2u e to the minus 2 over a u, by the way, I forgot to write it, evaluated between r minus r and r plus r. And then we get minus this other product, which will be a plus now, a over 2 integral from r minus r, r plus r, e to the minus 2 over a u du. So now let's solve this explicitly. So in the first one, we get minus a over 2. We evaluate the upper limit, so r plus r, e to the minus 2 over a, r plus big R, and then minus the lower limit, it becomes a plus, a over 2 absolute value of r minus big R, e to the minus 2 absolute value of r minus big R, divided by a. And now this one, we get minus a over 2 squared, right? Because when we integrate this, we get another one. And we get e to the minus 2au evaluated between these two boundaries. So what is that? So this is going to be minus a over 2 squared times e to the minus 2a over r plus r minus e over minus 2a over absolute value of r minus r. Okay, so let's plug it in. So that would be minus a over 2 squared e to the minus 2 over a r plus big R minus e to the minus 2 over a r minus big R. So it is almost the same as before, but the exponential is actually a little bit different. Okay, now just as before, let's factor out everything that goes with each exponential. So e to the minus 2 over a r plus big R, this has a factor of, actually, before we do that, we can actually factor out an entire a over 2, which will make everything simpler. Just as before we factor out a, now we have a over 2. So factoring out a over 2, we get e to the minus 2 over a r plus big R, factor of first this part, so we get minus r minus big R, and then this minus a over 2. So the same as before, basically, but with a over 2 instead of a. So we just like before, we can factor out the minus sign. So all of this is now positive. And then we have everything with e to the minus 2 over a, absolute value of r plus r. And then we get, let's see. So this part, which is r minus big R, and minus minus, so it will be positive, a over 2. Okay, great. So this is the result of the first integral, at least of that part, right? So we can now rewrite the direct integral. Actually, let me do it here. So the direct integral will be 2 over a cubed over r. And now we integrate from 0 to infinity of all of this dr. This time, unlike the previous time, there is no extra r that will multiply, and there is no extra e to the minus r as before. Okay, so as before, we need to separate the integrals, right? Because we have the dumb situation, or annoying, not dumb, but annoying situation of having the absolute value. And the absolute value, as mentioned, depends whether small r is larger or smaller than big R. So we have two cases: R smaller than big R, R larger than big R, right? And this is when 0 and big R, and this is between big R and infinity. So let's write it out. The first integral remains the same because there is no absolute value for the first part, right? Oh, by the way, we can pull out the a over 2. That's going to make it simpler. So this 2 goes away, and this is now a squared. Okay. So we have a minus sign in front, and then we have e to the minus 2 over a times r, and then e to the minus 2 over big R over a. And this is a constant, so we can actually take it out, just as before. So minus e to the minus 2r over a. And now comes all of this. So r plus big R plus a over 2 dr. And now comes the first of the other integrals from 0 to r. And in this regime, small r is smaller than r, and for that reason, the absolute value would be negative. So we need to put a minus sign in front. So we get e to the 2a, right? The minus sign in front cancels out that other minus sign, times r plus. Whoa, I just noticed, whoa, there's a mistake here. This is r minus r. Sorry about that. Sorry about that. That's a big mistake. Yeah, it's r minus r, of course. Okay, and then we have this thing, which will be big R minus small r plus a over 2. Okay, and well, I guess I don't really need this parentheses anymore. And here we can separate it as well. So we can write the exponent outside, at least the part that has the big R. So e to the minus 2 big R over a. Okay, and finally, we do the other part of the integral, the one that goes from 0 to infinity. And in this case, we leave it as it is. So e to the minus 2r over a times e to the 2r over a. But of course, this time, right? But of course, this time it is positive in sign. So we take the exponent out plus e to the 2r over a. And then we are left with the rest. So we get r minus big R plus a over 2. Okay, amazing. So now let's begin integrating. So just as before, let's call them I1, I2, and I3. Okay, so let's begin with the first integral. So I1, we will solve it as before by using the method of integration by parts. So let's use u is r plus big R plus a over 2. Thankfully, this time it's going to be much faster. There's no need to integrate by parts twice. And dv will be e to the minus 2r over a and dr. And v will then be minus a over 2 e minus 2r over a. So now the integral will be, of course, the product of these things. So first we get minus a over 2 times small r plus big R plus a over 2 times e to the minus 2r over a between 0 and infinity minus the product of these two. So we get minus minus, so we get a plus integral from 0 to infinity of a over 2 e to the minus 2r over a dr. So now let's begin finding the values for these things. So I1 will be, well, evaluated at infinity, this thing goes to 0. So we are only left with the second part, which will have a minus in front. So the minus goes away. Then evaluated at 0, this is 0. So we get r plus a over 2. And the exponential will also be 1. I mean, the exponent is 0, so the exponential is 1. And then we have this integral right here, which will be minus a over 2 squared e to the minus 2r over a between 0 and infinity. But at infinity, it goes to 0. So we're only left with when it is 0. In that case, the exponential is 1. And we'll have a positive sign here. So thus, we get ar over 2 plus a squared over 4 plus a squared over 4. So 2a squared over 4, or simply a squared over 2. Okay, so that is the result of the first integral. Now let's move to the next one. So I2, let's solve it here on the side. Whoops, I apparently erased the number 3. So I2 is this right there. So I'm gonna rewrite it here. So I2 is the integral from 0 to r of e to the 2r a big R minus small r plus a over 2 dr. So let's solve this once again by using, I'm going to zoom in a little bit so I use less space, by using integration by parts. So u is going to be r minus r plus a over 2. du will be d minus dr now because of that minus sign there. dv will be e to the 2r over a dr, and v will be a over 2 e to the 2r over a. So the integral I2 will be now the product of these two. So a over 2 times big R minus small r plus a over 2 e to the 2r over a between 0 and r. And then we get minus the product of these two. Minus minus is a plus. Integral from 0 to r of a over 2 e to the 2r over a dr. Whew, okay, now let's plug everything in. So evaluated at r, we get here that a over 2, r minus r is 0. So we get a over 2 e to the 2r over a, and then minus the same thing, but when small r is 0. So we get r plus a over 2, and this time the exponent is 0, so the whole thing is 1. So now this integral will be a squared over 4 e to the 2r over a between 0 and big R. And now let's evaluate it. So we get a squared over 4 e to the 2 big R over a minus a squared over 4. So let's put it in. So e to the 2r over a minus a squared over 4. Now let's multiply everything through so that we can simplify anything that we can simplify. A squared over 4 e to the 2r over a, we can see that we have it here and here. So we get 2 times this, so it will be a squared over 2. Then we have minus ar over 2 minus a squared over 4, but there's another minus a squared over 4 here. So we get minus 2 times a squared over 4. So simply minus a squared over 2. All right. So that is the result of integral number 2. Now let's go for integral number 3, which is that one right there. So let me rewrite it. So I3 is integral from 0 to infinity of e to the minus 2r over a r minus r plus a over 2 dr. Okay, so now again, integration by parts. U will be r minus big R plus a over 2. Du will be dr. dv will be e to the minus 2r over a dr. And v will be minus a over 2 e to the minus 2r over a. So now let's begin writing the integral. So I3, this is, now we can multiply these two, minus a over 2, r minus big R plus a over 2, between, well, and the exponent still, and between, wait, is this correct? Wait, there's a typo here. There's a typo here, sorry. This integral goes from r to infinity, not from 0 to infinity, of course. Yeah, so it is from r to infinity. Okay, sorry about that. I'll have to put a comment in to fix that. Okay, so this is from r to infinity. Okay. So then we have the second part, of course, the product of these two. So we get minus minus, so plus a over 2 integral from r to infinity of e to the minus 2r over a dr. Now this would be, at infinity, the exponential goes to 0. So we get the second part, minus minus is plus, a over 2, and then big R minus big R is 0. So we get this thing squared, e to the minus 2 big R over a. And then from this integral, we get a minus a over 2, which will square the existing one. And then e to the minus 2r over a between big R and infinity. So this will be a squared over 4 e to the minus 2r over a. At infinity, it goes to 0. So we are left with a plus a squared over 4 e to the minus 2 big R over a. So we can add them together and we are left with a squared over 2. There we go. We have all three integrals now. So let's now rewrite them. So I'll do it down here. The direct integral is 1 over a squared R times e to the minus 2r over a, and now comes, well, and with a minus sign in front. That doesn't look like a minus. And now comes the result, which is a r over 2 plus a squared over 2. That's from I1. Now from I2, I'm looking up here. plus e to the minus 2r over a times the result from I2, which is a squared over 2e to the 2r over a minus ar over 2 minus a squared over 2. And finally, we have plus e 2r over a times a squared over 2e minus 2r over a. So as you can see, there's going to be a lot of exponents that cancel each other out. So d will be 1 over a squared r, and then let's put everything that has e to the minus 2r over a. So that's going to be everything in here that has a minus sign in front. Don't forget about it. So minus ar over 2 minus a squared over 2. Then we have these. So minus a squared over 2 minus ar over 2. And then everything that doesn't have an exponent, which will be this a squared and this a squared over 2. So we get 2 times a squared over 2, or simply a squared. Good. And now we can simplify this even further. So 1 over a squared r, the exponent here, the exponential. And then we get minus ar minus a squared plus a squared. And finally, we can now multiply through 1 over, well, that's what we're going to multiply through, sorry. So we get this a squared divided by a squared r, so we get 1 over r minus, factorizing this minus sign, e to the minus 2r over a, factor of, now we get 1 over r, and then we have, actually 1 over r comes from this one, yes, and from this we get plus 1 over a. There we go. So this is the direct integral. Now, be wary, because in the textbook, Griffiths, he defines d as a times this, right? So if you want to go to what Griffiths has, you need to multiply and divide by a, okay? Because the way Griffiths did it is that, where did it come from? D. Here. The direct integral, there we go, here. He basically multiplied by a and divided by a, both of these. So the a in the denominator will go outside, right? And the a up there went into the definitions of d and x, okay? I'm going to add them later, but it is just so that you know where it comes from. Okay, and I think I'm just going to stick to his notation now. I'm going to make the change, at least in d, so that you can see. So basically d, according to Griffiths, right, d Griffiths is a over r, right? This is basically a times the d that we just found, right? Minus e to the minus 2r over a over big R plus 1. So that is the way in which he defined this. Okay, so this is the first of the two integrals. So this is integral d. Now we need to go to integral x. The good thing is that this is basically the same thing. There's very, very small changes. So integral x, right? It is psi g r2, 1 over r2, psi g r1. Okay, so basically this time the exponents won't be the same. So integral of e to the minus r1 over a, e to the minus r2 over a, square root of pi a cubed, but it's going to be squared, so the square root goes away. I think we've done it enough times now. Then we get 1 over r2, and then we have to put the whole spherical coordinates thing in. So let's use again r2 so that it cancels out at least a little bit. So r2 squared sine theta and then comes, of course, d theta. Well, let's write it as d3 for now. dr3. Okay, so as before, let's use this exact same change. So r1 will now be r2 squared plus r squared minus blah, 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 right? Exactly the same as before. So our integral will now, well, let's also solve the phi integral immediately. So we get 2 pi over pi a cubed. And then we get integral from 0 to infinity. This is r. Integral from 0 to, well, this time it isn't 0 to pi because we are already doing the change of variables. We're going a bit faster because it's literally the same that we have done 2 times already in this very video. And then we have e to the minus r1, or in this case, r2, which we will now simply call r as before. And now r1, which we will replace by square root of r squared plus, well, actually we haven't done the change of variables yet, I guess. 0 to pi. I have to change that in the next step. So this is plus r squared minus 2r r cosine theta divided by a. And then r2 sine theta d theta dr. Okay, so that's what we are doing here. And now exactly the same as before, we will say this thing right here is u. So u is going to be, or u squared rather, will be r squared plus big R squared minus 2r r cosine theta. 2u du will be 2r r sine theta d theta as before. So u du over big R will be r sine theta d theta. Okay, so plugging this thing in, we get 2 over a cubed times r, right, the one coming from there, integral from 0 to infinity, integral from r minus r, now we have to make the change, r plus r. We have an exponent that we can leave out here because that doesn't depend on the angle, right, this one. This r is gone, sine theta is gone, d theta is gone, so we are left with e to the minus u over a u du dr. So that's what we have. Now this integral we have solved so many times. I'm gonna go look for the result. So this is the result. Let's see, is it already factored out or not yet? It isn't factored out yet. So that is the result, but with a instead of a over 2. So the result of this integral will be the following. So this will be 2a cubed over 3. And again, we have done this once during normalization and once during the d integral. So this integral is all of this, which I factor out here. So that will be a factor of minus e to the minus r plus r over a factor of r plus a. And then we have the part with the absolute value, which will be e to the minus a, this is absolute value r minus big R over a. And then we have r minus r in absolute value, so plus a. So that is basically the result that we got before. And as I mentioned, this is exactly the same as before, but the main difference is that now our a, before we had a over 2, now we have a. So that really helped us save quite a bit of time. And the a that we factored out, we can cancel with what we have out here. So we get a squared. So now we do the same that we did before. We have to separate our integral in each of the limits, right? In each of the regions. So the first part doesn't have any issues at all, so we can simply leave it as it is. We can take out the minus sign, take out the exponent that has the big R, which is minus r over a, and we leave everything else inside. So e to the minus 2r over a times r plus big R plus a dr. And then comes the first integral, so between 0 and big R. And here, this thing is negative, so we need to put a minus sign in front. So we get e to the minus, well, we have minus r over a here, but positive here. So they actually cancel out, and we don't have a e to the r a inside. We only have one outside. So e to the minus big R over a. And inside, all we have is r minus small r plus a dr. Of course, here, because of the minus sign, these two are switched. And finally, we have integral from r to infinity. So now this is positive, no need to put a minus sign in front. So we get a positive e r over a outside. Inside, we get e to the minus 2r over a and r minus big R plus a dr. So now we have to solve each one of these three integrals. So as before, let's just call this I1, I2, and I3. So let's go. I3 we can solve as before by using integration by parts. So let's say u will be r plus big R plus a, du will be dr, and dv will be e to the minus 2r over a, and v will be, and dr of course, this will be minus a over 2 e to the minus 2r over a. So this integral, sorry, I don't know why I wrote I3, I meant I1. So this will be, let's see, this product, so minus a over 2 e to the minus 2r over a times r plus big R plus a between 0 and infinity. And then we get the product of these two with a minus. So plus, since it cancels out, integral from 0 to infinity e to the minus 2r over a dr. Okay, now let's evaluate this. So at infinity it goes to 0, so we are left with when it's 0. So this is positive a over 2 and then r plus a. And then we have this integral which will leave a minus a over 2, so we get a squared over 4 e to the minus 2r over a between 0 and infinity. But at infinity it is 0, so we only have the second part. The exponent elevated to 0 is 1, so we get positive. And here we have ar over 2 and a squared over 2. So we get a squared over 2 plus a squared over 4, which is 3a squared over 4. All right, so this is the result from the first integral. Now, the second one is going to be much simpler since it is simply a polynomial. So it's integral from 0 to r of r plus a, and then we have minus r dr. So this is simply r squared plus ar, right from here, and then minus r squared over 2. So adding this together, we get r squared over 2 right there. So that is the second one, very, very quick. Let's go for the third and final one. So the third integral, I3, we will once again solve by using integration by parts. So u will be r minus r plus a, du will be dr, and then we have, I don't think you can see that, dv, which is e to the minus 2r over a dr, as always. V is minus a over 2 e to the minus 2r over a. So now let's put everything in. So we get the product of these two, minus a over 2. Let me zoom in so we can focus on it. Minus a over 2, product with r minus big R plus a, e to the minus 2r over a, evaluated between r and infinity. And then we get minus this product. So we get plus a over 2 integral between r and infinity of e to the minus 2r over a dr. So now we can evaluate this part. At infinity, it goes to 0. So we get only the other part, a over 2. At big R, these two cancel out. So we get a and e to the minus 2 big R over a. Now here we get minus a squared over 4. And then e to the minus 2r over a between big R and infinity. Okay. So now we evaluate this. At infinity, it is 0. And at big R, we change this and this, right? It goes to positive and the small r to big R. So now we get 2 times, actually no, we have to add these two together, right? So we get a squared over 2 plus a squared over 4, which is 3a squared over 4, e to the minus 2r over a. So this is the result from the third integral. So now let's just plug everything into our expression for x. So x is 2a squared over r, and then minus e to the minus r over a, times the result from I1, which is ar over 2 plus 3a squared over 4. And then we get plus e to the minus r over a times the expression from I2, which is r squared divided by 2 plus ar. And finally, we get plus e to the r a times the result from the third integral, which is 3 over 4 a squared e to the minus 2r over a. So as you can see, every single one of these terms will be multiplied by e to the minus r over a. So let's factor it out. And let's see. So we get minus ar over 2 here plus ar here. So in the end, we get ar over 2. Then we have minus 3a squared over 4 plus 3a squared over 4. So they cancel each other out, actually. And then we still have this thing here. So we get plus r squared over 2. So now let's multiply through. So we get e to the minus r over a. And then 1a cancels out. R goes away, 2 goes away. So we have 1 over a plus r over a squared. Yes, 1 r over a squared. There we go. And now this is a slight difference from what you would see just as it happened with D. In the books by Griffiths, they defined x, right? X Griffiths is basically a times the x that we just found. So in Griffiths, it appears as minus r over a, 1 plus r over a. So that is x. So we finally found everything in our energy, in the expression for our energy, which is this thing right here. Okay, so now we have D, now we have X. And that is what was asked of you in Griffiths Problem 7.8. But we aren't done yet. So now we have to do the rest. We have to put everything together. So I'm going to do it to the side. So the expectation value of the Hamiltonian, this is E1 minus, then what do we have? Let me go back. We have 2a squared e squared. I think this is way too big, by the way, but well, 2a squared e squared divided by 4 pi epsilon 0 times a. Why times a? Because we had to include the a to use the same notation as Griffiths. And then we have the expression from D. So the result from D. So D plus X, right? And what is D and what is X? Oh, and I think we almost forgot Where did we leave the proton-proton part, by the way? Let's see. Oh, there it is. So the proton-proton part, as we discussed before, is simply e squared plus e squared over 4 pi epsilon 0 r. Okay, so there we have the proton part again. Now we need to plug everything back in here. So how do we plan on doing that? Well, thankfully, actually no, with a lot of effort, that's all that it's gonna be. So actually I'm gonna zoom in and do it like this. So we have E1, and then we have these bunch of, ugly looking numbers. But we know, right, that E1 is minus E squared 4 pi epsilon 0 times 1 over 2a. So if we look at what we have here, we have E squared 4 pi epsilon 0, we have a. We only need to multiply by 2 and divide by 2. So if we do that, we can rewrite that entire thing as just plus, then we will have 4 times E1 times a squared times everything else, okay? So that is what we want to do there. And now we need to plug in the result for D. So where is the result for D? It looks like I got rid of it accidentally, but don't worry, I have a backup. Oh, and by the way, this is E1. Okay, so D is A over R minus 1 plus A over R e to the minus 2R over A. By the way, in this, what we did here, including E1, is the reason why Griffiths had introduced this extra A into D and X, because the A was going to appear anyways. The thing is that he did it in kind of an unnatural moment. Okay, so that is D. And then we still need to add X, which is 1 plus R over A e to the minus R over A. Okay, but we also have A squared. Do you guys remember what A squared was? A squared is 1 over 2 plus 2i. So, okay, I'm completely lost here. So let's plug A squared in. That is 1 over 2 plus 2i. So 1 plus 2i. So we can, simplify this a little bit. There we go. Okay. And by the way, this is the same expression that Griffiths has in the book, in case you're wondering. We can, just to show it, we can factor this out. And we get 1 plus 2 over 1 plus, small mistake, this is just I. 1 plus I. 1 plus I times D plus X, right? This is times E1. This is the same as that Griffiths has in the textbook, just so that you can compare it. So now, we still haven't really introduced, we almost left out the potential here, by the way. Don't forget about this. So 4 pi epsilon 0 r. I've been treating it a bit, I've been leaving it alone because Griffiths for some reason decided to do so. I don't really know what's the point, why he left it alone. I mean, I guess because it's easy to work around. But anyways, we can also rewrite this thing in the following way, right? Because we want to also leave it in units of E1. So here we are almost there, right? We have E squared 4 pi epsilon 0. So we have this thing. So E squared 4 pi epsilon 0, this is minus 2a times E1. So let's write that in its place. So that is minus 2a E1. So minus 2a E1. And there is still an R floating around, by the way, that one. So there we go. So, to this we will add the proton-proton interaction. Okay. I wanted to leave it separately because Griffiths did it, and in case you're following the book, I wanted to show it. Also, it is a constant amount that is easy to calculate. That's also why it makes sense to leave it on the side, but you can't forget to re-include it at the end. Okay, and I, what was I? I is this thing, e to the minus r over a. So I'm going to write it here. I is e to the minus r over a, 1 plus, I think it's r over a plus like r over a squared 1/3, or was it the other way around? Let me check. So I is, yes, it is this. So now we need to plug everything into the Hamiltonian. So doing that, let's see. We have, well, 1, that is easy, plus 2, I will factor out the E1, that's what I'm doing here. And then I have a over r minus 1 plus a over r, e to the minus 2r over a, plus 1 plus r over a, e to the minus r over a. And then we still have the minus 2a E1 over r. Well, the E1 I'm going to factor out, so I guess I shouldn't write it. And this part right here is being divided by 1 plus e to the minus r over a, 1 plus r over a plus r over a squared times 1/3. And all of this is in units of E1, right? It's multiplied by E1. Okay, so now it's working with this by hand is not going to be easy. So let's write it out a little bit neater, a little bit cleaner, and then use software to study the equilibrium point. So let's call something, look at it, there's r over a, r over a, r over a, r over a, and r is our variational parameter. So let's call r over a x, right? That way we can clean up the notation a little bit and we can get the following. So we get 1, and then let's see, plus 2, 1 over x minus 1 plus 1 over x e to the minus 2x plus 1 plus x e to the minus x. And all of that is divided by 1 plus e to the minus x and 1 plus x squared divided by 3. And then you have minus 2 over x here on the side, E1. So to simplify this, let's do the following. So let's take minimum common denominator. We can leave the 1 here. But this minus 2 over x, let's take minimum common denominator. And just so that we have to do fewer things, this 2 right here, let's just factor it out from, keep it factored out here, but also factor it out from there. So we will have 1 plus 2 times, and then everything that was already in here, so minus 1 plus 1 over x, e to the minus 2 over x, plus 1 plus x, e to the minus x. And now we have minus 1 over x times everything that is down here. So 1 over x plus e to the minus x, and then minus 1 over x, everything that is in here. So minus 1 over x minus 1 minus x over 3. And all of that is still divided by 1 plus e to the minus x, 1 plus x squared over 3, and all of this is times e1. All right, so let's see, does anything cancel out? Yes, we can see that 1 over x, they cancel out. Then we have minus 1 in here and plus 1 in here. And then we can add these together. We can't really cancel them completely, but they do add. So let's do this step by step. So 1 plus 2. In here, nothing really changes, does it? No, nothing changes in there. So we get minus 1 plus 1 over x e to the minus 2x. And then we have plus. This is going to be the part with the e to the minus x. So we have minus 1 over x, and then x minus x over 3. So we get plus 2x over 3. And all of this is divided by 1 plus e to the minus x, 1 plus x squared over 3. Times e1, of course. Okay, so there's a lot of 1 over x's in here as well. So we could try to factor it out, right? So let's factor out 1 over x and also a minus. There's minus here, minus there. So 1 minus 2, and then we over x, right? And then we get, this has to be an x now, so that when we factor out 1 over x, it cancels out, plus 1 e to the minus 2x plus e to the minus x. And then this is now 1. And then minus 2x squared over 3. All of this divided by the same thing. All right, so this is now looking much cleaner. What we can still do, it isn't really necessary, but we are now going to define this new function, which will be f of x, which will be what we have here, but we're going to factor out a minus sign and leave out the e1. So basically f of x will be in units, so units of f of x will be minus e1. And by doing that, this will be minus 1 plus 2 over x, and then I'm going to do it like this. So 1 minus 2x squared over 3 e to the minus x plus 1 plus x e to the minus 2x. All of this 1 plus e to the minus x, 1 plus x squared over 3. And this is precisely what is in Griffiths' book. So that's how you get to that. So I made a quick code to be able to run this, right? To show you what the graph looks like. And this is what it looks like, okay? This right there. So as we can see, as x increases, there will be, and remember, x is r over a, right? The separation of the protons divided by the Bohr radius. And the units here are minus the ground state energy of hydrogen. So if this line here at minus 1 is E1, because Fx is in units of minus E1, and this here is minus 1. So at this point, the energy is E1, which is the energy of the ground state of hydrogen. And for there to be a bound state, we need that in the system with the proton, there has to be a lower energy than that, right? So that it remains stable. And we can see that within this range, right, 1 comma something, you could find this numerically if you're really interested. In that case, we indeed have bound states. So yeah, the hydrogen molecule ion is indeed viable, and this is what it looks like. And I hope this was helpful. This was quite a something. This took a while. Thank you if you got to this point. It was mainly just annoying integrals. If there's any question, make sure to leave know in the comment section. Please do leave a like on the video and comment and subscribe if you got to this point. I mean, it took a lot of work to get this done, so I'd really appreciate it. So as always, thank you for watching, and I'll see you in the next video.